panorama of partial structures that we have nowadays. And I hope I will be able to clarify this during the presentation. And well, since the globalization question is one of the relevant questions in the field, it seemed natural to us to attack it from the point of view of geometric partial comodules. But since I arbitrarily assume the audience today would not be particularly familiar with partial structures, I will begin with a short introduction on partial actions of groups, just to develop a bit of intuition. Then I will speak about geometric partial comodules, and I will present to you our globalization theorem for this, which is important essentially because on the one hand, it allows us to recover a number of known results, a number of known globalization theorem. And on the other hand, because it provides necessary and sufficient conditions for the existence of a globalization and an explicit construction of the latter whenever it exists. And finally, we will test the globalization theorem on at least a couple of concrete examples. But let us start with partial actions of groups. Very informally speaking, these are groups acting by partial bijections instead of global ones. But a bit more formally, these are partial functions from G cross X to X, where this G bullet X can be interpreted as the subset of the composable pairs, which satisfies a number of properties. Namely, the neutral element of the group is allowed to act everywhere, and it acts as the identity. Okay, this is expected. Whenever an element G is allowed on act on an element X, G to the -1 is allowed to act on the result. And the final outcome is the element, the starting element X again. And last but not the least, these partial actions are associative wherever it makes sense to be associative. Just to give you a toy example to see what is going on, imagine to take the circle group and let it act on a pair of tangent circumferences by rotation of one of them around its center. This is, well, one can check that this satisfies all these conditions for being a genuine partial action. But probably the most important source of examples of partial actions is provided by restriction of global ones. Namely, the idea is we have a group and we have a G set and we have a global action, and we want to restrict in a clever way this global action to a subset, which is not necessarily stable. Of course, we do not expect to find a global action again, but what we get is what is called a partial action. And we call this procedure inducing of the partial action. So this is the induced partial action. Again, just to have a toy example, imagine to take the usual circle group, let it act on the torus by rotation around the vertical axis, and imagine that we restrict it to these two circumferences, the red one and the blue one. I hope it's clear, any element of the group can act on the red circumference, but just the neutral element can act on the blue one. So if we draw the two circumferences on the plane and we see the outcome of this restriction procedure, then we exactly recover the partial action I showed you a moment ago. So for the moment, our unique example of a partial action is a particular instance of this induction procedure. One may wonder if this is always true or not. And this question is exactly the philosophy underlying the globalization procedure. So given a partial action of a group on a set, we call globalization a bigger set with a global action of our group containing the starting carrier in such a way that the induced action on the one hand and the original partial action coincide. And of course, we want this Y to be universal in the sense of being minimal initial among all the G sets satisfying this property. And the important or curious fact in this setting, which has been the origin of the study of globalizations, is that for partial actions of groups, this is always possible. We can always construct a global G set containing X, which induces the original partial action and which is universal as we said above. And just to close the circle, the torus I showed you a moment ago is in fact the globalization of the partial action of the beginning. And with this, let me close the parenthesis about partial actions. I just want to conclude by mentioning that partial actions of groups are just the tip of the iceberg. In fact, what happened is that as global actions of groups have had and still have great fortune in mathematics, the same is happening for partial actions. Over the last 25 years, we have experienced a true proliferation of partial structures. So we don't only have partial actions of groups on sets, topological spaces, algebras, sister algebras, and so on and so forth, but we also have partial modules over Hopf algebras, partial comodules, partial comodule algebras, partial representation, etc., 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 etc. So at this point, I hope it's clear why we need more general framework setting in order to deal in a unified way with all these different but still similar partial structures. And this framework has been offered to us by these geometric partial comodules. These have been introduced by Joost and his PhD student Jai Wei a couple of years ago. Their aim was to understand partial actions of fine algebraic groups on affine sets from a Hopf algebraic point of view. But we realized quite soon that they are a notion flexible enough to allow us to recover many of the partial structures I showed a moment ago. But to convince you of this, let me tell you what these geometric partial comodules are. First of all, they can be defined over an arbitrary coalgebra in a monoidal category with pushouts, where by monoidal category, I simply mean a category with a tensor product, which is associative and unital. And by the way, in what follows, I will always assume it to be strictly associative and unital. And a coalgebra is an object together with a coassociative and co-unital comultiplication. And once given this data, we call geometric partial comodule a cospan over an object X of this form, where this leg here is an epimorphism, and that you can imagine it to be a kind of partially defined coaction, which is co-unital in the sense that these two cospans are the same up to isomorphism, and it is coassociative in the sense that these two big cospans are the same up to isomorphism again, where all these squares are obtained by push-out procedure. Of course, you may imagine we can define morphisms of geometric partial comodule and construct the category of geometric partial comodules, but let me go further and convince you that this notion is really flexible enough to deal with many of the examples we have seen a moment ago. And the flexibility lies in the choice of the underlying category. So for instance, if we choose the opposite of the category of sets, partial actions of groups are geometric partial comodules in the category of sets, in the opposite of the category of sets. But this is not the only one. If we can also recover partial actions of monoids, partial actions of topological monoids, topological spaces, partial modules and comodules over Hopf algebras, partial comodule algebras, it just depends on choosing in a clever way the underlying category. And now, in order to be able to speak about globalization, we still miss one ingredient, which is the induction procedure. So let me tell you that whenever we are given a comodule over our coalgebra in the underlying category and we have an epimorphism to any other object, one can take the span above and perform the push-out. The resulting cospan is a structure of geometric partial comodule over the carrier X. And well, you may imagine this is just inspired by what is happening in groups for partial actions of groups. And now that we know how to induce a geometric partial comodule structures, let us see what it does mean to globalize a geometric partial comodule structure. Again, as you probably expect, a globalization for a given geometric partial comodule is a global comodule together with an epimorphism such that the induced geometric partial comodule structure and the original one are the same. So this induction square commutes and it's a push-out square. And of course, we want Y to be universal, in the sense, in this case, to be terminal among all the global comodules satisfying this property. And we call geometric partial comodule admitting a globalization globalizable. We can, of course, consider the category of globalizable geometric partial comodules inside geometric partial comodules. But anyway, the important question now is if geometric partial comodules are globalizable or not. And here is where our globalization theorem enters the picture. Actually, what we proved is that geometric partial comodule is globalizable if and only if this particular equalizer exists in the category of comodules. And this is what is providing us the global object, the candidate globalization. And of course, we want the original geometric partial comodule structure to be induced by the new global comodule that we have found. So we want the induction square to be a push-out diagram. And notice that if these necessary and sufficient conditions are satisfied, then our equalizer is exactly the globalization of our starting geometric partial comodule. So this is what I meant when I said that it provides necessary and sufficient condition and an explicit construction of the globalization. And now let us test it on a pair of concrete cases of interest. Of course, the first one is the case of partial actions of monoids, the one we started with in some sense. In this case, essentially, the geometric partial comodules in the opposite of the category of sets are exactly the partial actions of monoids. This is the nicest category one can work with because independently on the monoid we choose, the two necessary and sufficient conditions are always satisfied. So any partial action of a monoid can be globalized. And in fact, in this way, we recover a well-known theorem by Megrelishvili and Schroeder, in which they provided a concrete construction of the globalization. And this is also consistent with what we have considered a moment ago, because their explicit construction is exactly the co-equalizer of the canonical pair of maps. So their theorem is exactly a particular instance of our construction in the opposite of the category of sets. And if we restrict further our attention to partial actions of groups, we also recover the globalization theorem by Abadi that I showed you at the very beginning. But I mean, we introduced new objects, we proved new theorems, we expect to be able to do new mathematics, not just recover something that is already known. So let us see something original. Let us see what happens if we consider geometric partial comodules into an abelian monoidal category. Again, this is probably not the best, but it's already a very good framework where to work with, because 1.5 of the two necessary and sufficient conditions are always satisfied in this setting. Actually, we can always compute the equalizer in the underlying category. The induction square is always a push-out square. The only half of the problem we need to take care of is the fact that the equalizer has comodule structure. But if we are lucky enough to be working in a category, or sorry, to be working with a coalgebra, such that the category of comodules admits the equalizers and the forgetful functor preserve them, then our globalization theorem gives the best, and it gives us that all the geometric partial comodules are globalizable. And it also gives us a globalization, a concrete construction of the globalization. And as particular instances of this theorem, we recovered, for instance, the standard dilation for partial modules over Hopf algebras, which has been introduced by Alves, Batista, and Yost something like 5 years ago. We recover the globalization for partial representations of finite groups that we used in a paper with Michele and William recently. We provide a brand new globalization for partial comodules over Hopf algebras, which was not existing before. And we also find a new globalization for partial comodule algebras. And the only detail here is that it does not coincide with the enveloping coaction provided by Alves and Batista a few years ago, but not because one of the two is wrong. It's simply because our globalization satisfied the dual universal property with respect to their. They were really looking for a minimal enveloping coaction in the sense of initial with respect to inclusion. We are looking for terminal globalization with respect to the property of inducing the geometric partial comodule structure over the target. And okay, this was everything I wanted to tell you. So thank you very much, and let's enjoy the time which is left.
Thanks, Paolo.